Everybody, and welcome back to another fun and exciting pre-calculus class. We're getting close, 16.3, only a few lessons left, so hang in there. Application of the first derivative. So in the last lesson, we learned what the first derivative was, how we can figure it out. In this lesson, we're actually going to talk about how we can use it and apply it. All right, so here we go. We have the application of the first derivative, instantaneous velocity. Now, there's a couple different types of velocity. First of all, velocity is probably the one that you're used to dealing with at this point, maybe through a physics class that you've taken, or just in maybe an upper level science class of some other type. You've learned about average velocity or just velocity. So velocity equals distance over time, or even more specifically, you could say the change in distance over time, or the change in your time over the distance that it's happening, or more specifically, the change in the distance over the change in the time. If you put this on an x and a y axis, which you see down here, you'll see that it graphs out basically like any other type of a curve that we've put on a graph. So like a parabola or something else. Now it doesn't finish off and go the other way, but it looks like some sort of a curve that we've seen before. This is called average velocity. We're going to do one of these average velocity problems, and then we're going to take it kind of to the next level and use the first derivative to find what we call instantaneous velocity. But let's just take this problem right here. Example number 1. In this function, the distance equals 0.02 t squared minus 0.4t plus 1. This function gives distance an object travels in meters. Draw its graph and time, and then, basically they kind of already draw it out, so we can look at it. All right, so here's the chart we'll be using. This gives us all of our data points, our information. If you notice, they've graphed each one of these. So there's 1 on the t. The t is going to be our x-axis, and the dt distance is going to be our y-axis. And so 0.8, and then there's 1, and then it kind of goes up from there. So there's the information. And what we need to do is we need to plug into this formula. The formula is the change in distance over the change in time. So, for example, if we're going to do this first one, so let's come over here to the computer and let's look at it over here. So, if we want to find the average velocity between these two time intervals, so between 2 seconds, so this one right here, and 6 seconds, this one right here. Basically, think of this as during this block of time. What was our average velocity? How fast was this thing going during this block of time? So what we have to do is we have to take the change in those two things. So if we take the change going from, and you can kind of think of it, we're going from 2 to 6. So we want to start with 2. So technically you can write this either way. The book starts with 6. I'm going to start with 2. That way you can kind of see it working the same way. So 2, the distance for 2, the dt for 2 is going to be 1. So then 1.0. And then we're going to subtract out, we're going to change this to go from 1 to 5.8. 1 minus 5.8. And this is all going to be over our change in time. So this time right here was from 2 seconds, and then this time right here was 6 seconds. So when we go ahead and subtract that out, we're going to get 1 minus, that's going to be a negative 4.8. And that's going to be over, that's going to be a negative 4. Notice we have a negative, that's why I said either way you put it, it will work, because the other way would have kept your fraction positive, but this way we have negative, which means positive, so we have a 4.8 over a 4. Now we would just go ahead and divide that out, and when you divide that out, you get 1.2, and it said that it was in meters per second. So that's how you do the average velocity. Okay, and that should look fairly similar to things that you've done in the past. Let's go back over here and look at the page again, and we'll kind of go through some of these other ones. It also asks you to do from 4 to 2, and there's the math on that one. And then it asks you to do from 3 to 2, and there's the math on that one. In other words, it's saying what's the average between these two things. And that's good and all, but what if I want to know how fast or what was my velocity when I was going 2.5, like in this exact spot? Well, what that means is it's like, here's what it is. It really would be the tangent line. It's my slope tangent line right here at 2.5. But I don't have a slope line there. I don't have a tangent there. How could I put that in there? How could I mathematically figure that out? Well, turn the page. This is what's called instantaneous velocity. That's what we're looking for in this lesson. We're looking for the idea that I could say, okay, at this specific point, what was my velocity? Okay, not what was my average between these 2 points, but specifically when I was going exactly 2.5 seconds, for example, what was my speed at that time? Okay, the way that we would do that is we use the first derivative. Notice it says instantaneous velocity equals the first derivative of the distance time function. So it also equals the slope because we said that the first derivative equals the slope. So if we can find the slope of that point at that exact point right there, 2.5, for example, whatever point we're looking for, that's what we want. Okay, now here's the question. The question says, using that same example, using that same formula, find the equation for the instantaneous velocity. That's the first part. So we need to find the first derivative. Secondly, it says find the instantaneous velocity at 2.0 seconds. All right, so let's go ahead and bump back over here to the computer and let's take a look at some of these things and we'll kind of do this together. So these are some things that you should definitely write down. The slope of the line at a specific point in time is called instantaneous velocity. You could also say that is the first derivative. So what is the question asking for? Let's find the first derivative and let's find its velocity at 2 seconds. So here we go. How do you find the first derivative? We have to go back to last lesson. What did we learn in last lesson? We learned that you find the first derivative by doing what? There was 2 steps. The first step is taking this exponent and multiplying it times the coefficient. So what is that? In this case, we have 2 times 0.2. That's going to be 0.4. So we would get 0.4. That's going to be our new coefficient. And then the way that we did this, it said the next step is to take the exponent and subtract 1. So 2 minus 1 is 1. So just a t. And then minus, we do the same thing. That's a 1 here. So 1 times that is going to be 0.4. And then the t goes away in that case. And the 1 is going to go to a 0. So this is the first derivative right here. So we would call this d prime t. That's how we would write that. And then what would we do next? All we would do from there is the one that we're looking for is what? We had that the t equaled 2.0. That's the one we're looking for. So we're going to plug that t in there. So we're going to get d prime 2.0. There should be an equal sign there. Equals 0.4t, which is 2.0, minus 0.4. And if we solve that, we'll know what our velocity is at this exact moment of 2.0 seconds. All right, so just go ahead and plug that into your calculator. 0.4 times 2 equals minus 0.4 equals, still get a fraction on mine, but I can change it to a decimal. 0.4 would be the answer. So in this case, it would be the velocity, not just velocity, the instant velocity would equal 0.4. And that would be meters per second again. Now here's the cool thing. We could use that same formula that we just figured out, which would be the d prime of t, or the instantaneous velocity formula for this distance time function, and we could plug anything that we want into it and we would find the answer. For example, if we wanted to know, and things that aren't even on our chart, right? So things that are not on our chart are things like 12 seconds. How fast would we be going if we continued that same kind of trajectory up? Now, obviously, based on physics and different things, we can't just keep going and going, or else we'd be able to go infinitely fast. You can't do that. You have different things that slow you down. So there's a lot more to figure into an equation like this, but for just kind of these basic pieces and components, there you go. Find the derivative and then plug into the derivative. So that's a little bit shorter lesson than maybe you're used to, and maybe you deserve that because you've been working hard. So kind of a simple little lesson here. Find the derivative, plug into the derivative, and you should be able to get the answers to these things. And maybe you're thinking, wow, calculus is so easy. I can't wait to take calculus. I hope you're thinking that. I really do. Because it's not as hard as a lot of people think. It just has this kind of the stigma like, oh man, calculus is a college class. It must be really hard. Okay, it's really not if you keep your progression. So if you were in Algebra 1, you did well. Algebra 2, you studied and you worked hard. And, pre-calculus and trig and geometry and all those things, if you've kind of kept up and maintained your math to this point, calculus is just going to be another step that you just step right into. And yeah, it might be a little bit challenging, but you're going to be fine. Okay? Don't worry about calculus. You'll be fine. So keep working hard. Do your best. That's all I've got for you. Make sure if you missed anything, you slide it back and you watch it again. We'll see you later. Have a good one. Bye-bye.